This is SpaceTime, Series 20, Episode 43. Coming up on SpaceTime, black holes prove Albert Einstein right again, NASA's new mission to touch the Sun, and a possible Quark Nova. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new black hole study has once again shown Professor Albert Einstein's general theory of relativity to be correct. The new research, reported in the monthly notices of the Royal Astronomical Society and on the pre-press physics website archive.org, confirms that stars being consumed by black holes really do fall through an event horizon into a singularity, rather than simply crashing onto some sort of hard object. Black holes are immense gravity wells, so dense that the escape velocity from one is greater than the speed of light. And as there's nothing which travels faster than the speed of light, other than the accelerated expansion of the universe itself, nothing, including light, can escape a black hole. The biggest black holes are commonly found at the centres of galaxies. Sagittarius A star, the supermassive black hole at the centre of our own galaxy, the Milky Way, is about 4.3 million times the mass of the Sun. Most scientists agree that black holes are surrounded by things called event horizons. They're sort of like points of no return, inside of which matter and energy will fall forever into a black hole singularity. Although widely believed, the actual existence of event horizons has never been proven, and some theorists have suggested that there's something else there instead, not a black hole, but an even stranger supermassive object, which has somehow managed to avoid gravitational collapse into a singularity surrounded by an event horizon. The idea is based on modified theories of general relativity, Dr. Einstein's theory of gravity. While a black hole singularity has no surface area, this hypothetical collapsed object would have a hard surface. So any material such as a star, for example, being pulled in wouldn't actually fall into a black hole, but instead splat against a hard surface and be destroyed. At least that's the hypothesis. Now astronomers from Harvard University and the University of Texas at Austin have put a basic principle of black holes to the test, showing that matter does completely vanish when it's pulled in. Their results therefore provide a successful test of general relativity, just the way Einstein intended. One of the study's authors, Professor Pawan Kumar from the University of Texas, says the whole point of the exercise was to turn this idea of an event horizon into experimental science, and to find out if event horizons really do exist or not. The authors came up with a test to find out if there really is any hard evidence supporting the existence of an event horizon around the black hole. The team first had to work out exactly what the telescope would see were it watching a star hit the hard surface of some sort of hypothetical supermassive object at the centre of a nearby galaxy. In other words, would there be a visible splat? It turns out gas from the star would envelop the object, shining for months, perhaps even years. Once they knew what to look for, the authors then had to work out exactly how often something like this should be seen in the nearby universe, that is, if the hard surface hypothesis was correct. Firstly, they needed to estimate the rate at which stars were likely to fall into supermassive black holes. Although nearly every galaxy has one, the authors only considered the most massive black holes, 100 million solar masses or more. They concluded there'd probably be about 1 million or so of them within a few billion light years of the Earth. They then searched a recent archive of observations by the 1.8 metre Pan-STARRS telescope in Hawaii. Pan-STARRS is undertaking a project to survey half of the Northern Hemisphere sky. The telescope scanned the hemisphere repeatedly for some 3.5 years, specifically looking for transients, that is, things that glow for a while and then fade. Their goal was to find transients with the expected light signature of a star falling towards a supermassive object and then splatting hard against the surface. Now, given the rate of stars falling into black holes and the number density of black holes in the nearby universe, the authors calculated how many such transients Pan-STARRS should have detected over its 3.5-year survey. It turns out Pan-STARRS should have detected at least 10 of them. That's if the hard surface hypothesis is correct. However, in reality, they found none. The findings mean black holes probably really do have event horizons, and that material really does disappear from the observable universe once pulled inside one of these exotic objects, just as expected according to general relativity theory. So, it seems general relativity has passed another crucial test, yet more proof that it's never wise to bet against Einstein. As for the authors, well, they're now proposing to improve their test by using an even larger telescope, the new 8.4 metre Large Synoptic Survey telescope, now under construction in Chile. Like Pan-STARRS, the Large Synoptic Survey telescope will make repeated surveys of the sky over time, revealing new transients, but with much greater sensitivity. You're listening to Space Time. I'm Stuart Gary. The United States is to send a spacecraft into the Sun's upper atmosphere, the corona. The Parker Solar Probe will quite literally touch the Sun, travelling within 5.9 million kilometres of the Sun's photosphere, its visible surface. The mission, which will make its closest approach to the Sun on December the 19th, 2024, will try to determine why the corona reaches temperatures several millions of degrees hotter than the Sun's surface temperature of about 5,800 degrees Celsius. Science's current best hypothesis involves a process called magnetic reconnection, in which magnetic field lines snap and reconnect, releasing huge amounts of energy in the process. The mission will also try to better understand the solar wind, the constant stream of charged particles emanating from the Sun, which floods the solar system. Massive eruptions on the Sun, such as solar flares and coronal mass ejections, can turn the solar wind into powerful geomagnetic storms or space weather. These solar storms often damage or destroy spacecraft by overloading their delicate electronics. They also cause fluctuations in the Earth's atmosphere, making it contract and expand. That changes the density of the rarefied particles through which satellites fly. Consequently, it can increase atmospheric drag on spacecraft, causing them to use up more fuel in order to prevent orbital decay, ultimately shortening their lifespan. The intense radiation generated by geomagnetic storms also poses a very real health threat to the safety of astronauts. For us on the ground, space weather also disrupts communications and navigation systems. It forces aircraft to deviate from polar routes, and it overloads terrestrial power grids, causing widespread blackouts. Originally named Solar Probe Plus, the 810-kilogram car-sized spacecraft has been renamed the Parker Solar Probe in honour of Professor Eugene Parker, the astrophysicist who first predicted a supersonic solar wind and also the spiral shape of the Sun's magnetic field in the outer solar system. NASA says it's the first time they've named a spacecraft after a living scientist. The mission is slated for flight on July 31st, 2018. The mission will use 7 gravity-assist slingshot manoeuvres around Venus to incrementally decrease the orbital perihelion of the spacecraft in order to achieve 24 passes through the Sun's corona down to approximately 8.5 solar radii. The spacecraft, which is being built by Johns Hopkins University, will use a special solar heat shield to survive the extreme 1400 degrees Celsius temperatures during its close encounter with the Sun. That's some 520 times the solar intensity experienced in Earth orbit. The reinforced carbon-carbon composite solar shield mounted on the front of the spacecraft will shade the probe systems and scientific instruments from direct sunlight. As the probe shoots around the Sun, it'll achieve speeds of over 200 kilometres per second, in the process becoming the fastest man-made object ever built. To find out more, Andrew Dunkley speaking with Dr. Fred Watson from the Australian Astronomical Observatory.
It certainly captured the imagination of people around the world. I've seen a lot of news reports and read a lot of news reports about this mission to, and I quote NASA here, to touch the Sun, which sounds like a pretty dangerous exploit, and I'm guessing it's not a manned mission.
Well, that's right. So what did the first astronaut say who touched the Sun?
Ouch.
And the answer is, ouch, 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 ouch.
Well, in the modern vernacular, he probably was a bit more descriptive, but we won't go there.
Yeah, that's right. I actually, I think a mission to touch the Sun is slightly exaggerating, because in a sense, we are all touching the Sun, because we're bathed with this stream of subatomic particles from the Sun. In a way, we're all part of the Sun's atmosphere. But I do get what they're talking about, because this spacecraft, when it makes its epic trip to the Sun in 2018, will actually, by a factor of 7 times, I think, be closer to the Sun than any other spacecraft that's ever been sent into the inner solar system. So its minimum distance from the Sun will be about 6 million kilometres. Remember, we're 150 million kilometres from the the sun.
Yeah.
So it's quite clearly
Definitely
much
close.
closer. It's definitely close. At that distance, of course, the radiant heat from the sun will be very, very high. And they're expecting that the spacecraft will encounter temperature in its environment or be heated to temperatures in the region of 1400 degrees Celsius. So they have a carbon fiber heat shield, a carbon composite heat shield. This is a 100 millimeter thick heat shield, which the spacecraft will kind of hide behind. And its instruments will sense the atmosphere around it. And I might mention that it will not have cameras on board because it's not going to be taking images. But I think the Europeans are also sending a spacecraft to the sun that will actually peep through slots in its heat shield to take images of the surface of the sun with a resolution that we've never seen before.
You'd want some heavy filtering on the lens.
Exactly.
I reckon otherwise you're just going to have, look at that beautiful white picture of nothing.
Yes, that's right. It would be white, very white indeed. Anyway, so that there is a European venture which we'll probably hear about in due course, which will not be as close to the sun, but will actually kind of supplement what this NASA probe is doing to tell us about the atmosphere of the sun, because there are huge questions that still remain. It's our nearest star by a very long way, and we do understand it, I think, remarkably well, given what the understanding of the sun was when I started taking an interest in astronomy. Believe it or not, 60 years ago, Andrew.
No.
That's when I started getting hooked on all this, and we just thought the sun was a big ball of gas then that didn't do much except shine. Now we know it's riddled with magnetic fields. We know it has an atmosphere, an outer atmosphere, what we call the corona, which is what you see during an eclipse, by the way, this beautiful ethereal white structure, often sort of delineated with magnetic field lines. That is what you see during an eclipse. The thing about the corona is its temperature is vastly greater than the temperature on the surface of the sun that we see, which we call the photosphere. That surface is at about 5,000 degrees Celsius, but the corona is up to 1,000,000 degrees.
Oh, what?
We don't understand how that heat transfer works between the surface of the sun and the outer corona. How does it get to be so hot?
It's a convection oven. Yeah, that's what it is.
Well, it may well be. We think it's probably to do with magnetic fields, but really nobody knows. And that's perhaps the main reason why Solar Probe Plus is being sent. The other one is to work out really where these subatomic particles come from that permeate the environment of the sun, the solar wind, which plays such an important part in earthly life because we see aurorae when there's a strong solar wind. We suffer sometimes communications and power blackouts when the solar wind really starts blowing a gale. Back in 1989, I think something like 9 million people lost their electricity supply in Canada because of the solar wind being very strong, and essentially it was a geomagnetic storm. Where does all that come from? We don't know. So Solar Probe Plus, we hope, will help to answer some of those questions.
And one of the great concerns in the modern era, because we're so reliant on electricity and digital technology, is an electromagnetic pulse from the sun.
Yeah, that's right.
Destroying our electronics. It's a known concern. It's a known problem. And even in little towns like mine, the emergency services departments have actually got this on their emergency list as a potential problem for the future.
Yep.
So, and it could happen any time. So
that's right. There you go. So that understanding all that and perhaps allowing us to predict it better, that might well be of assistance to everybody.
One final question: how long does the trip take from Earth to the sun by rocket?
My recollection is, I looked at this a few days ago, I think it's something like 220 days or thereabouts.
Wow.
To get into that close proximity. As I understand it, it will be a sort of flyby mission. This spacecraft will actually whiz past the sun at the closest point in its orbit and then continue its orbit, basically taking it back out to the Earth's orbit. I don't know whether the plan is to see how well it survives the first pass, and if it does okay, send it back again.
Yeah.
But it will probably wind up in orbit around the sun in any event.
That's Dr. Fred Watson from the Australian Astronomical Observatory speaking with Andrew Dunkley on our sister program, Space Nuts. And this is Space Time. I'm Stuart Gary. If you want more Space Time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTime with Stuart Gary on Instagram, And on Facebook, just go to www.facebook.com/spacetime with Stuart Gary. Astronomers are looking at the possibility of a new and very different type of trigger for a strange type of supernova event. Core collapse or Type II supernovae are usually generated by the explosive cataclysmic death of a massive star. After exhausting its nuclear fuel supply, the balancing act of hydrostatic equilibrium, in which the inwards pressure of gravity is balanced by the outwards pressure of nuclear fusion, comes to an abrupt end, and gravity wins. The star then collapses in on itself, in the process producing an explosion powerful enough to briefly outshine an entire galaxy, a supernova. However, astronomers think that one unusually powerful supernova, known as SN 2006 GY, may have been very different. SN 2006 GY exploded back in August 2006 in a galaxy called NGC 1260, located some 238 million light-years away in the Perseus cluster of galaxies, which is part of the Pisces-Perseus supercluster. At the time, SN 2006 GY was the most energetic supernova ever recorded, and at least 100 times more luminous than a typical core collapse supernova. Unusually, it continued to shine brightly, radiating energy for more than a year. And that's very strange, because supernovae usually reach peak luminosity for a few days before gradually fading over time. The weird light curve of SN 2006 GY got astronomers scratching their heads. It was far too bright in visible light for a typical core collapse or Type II supernovae, the type produced by the death of the most massive stars. And also it generated too few X-rays for a thermonuclear or Type Ia supernova, the type produced when the dead remains of a smaller sun-like star, called a white dwarf, explodes after drawing too much material off a companion star. Astronomers are speculating this all means that SN 2006 GY may well have originated as a very rare and extremely massive star, possibly as much as 130 to 250 times the mass of the Sun. Stars in this mass range are thought to have been common in the very early history of the universe. They were the very first stars to have formed, sparking the epoch of reionization some 13.4 billion years ago, the process which made the universe transparent and look the way it does today. The problem is such large stars, known as population 3 stars, were only thought to have been possible because they have extremely low metallicity. In astronomy, everything other than hydrogen and helium is considered a metal. In other words, these stars were formed almost exclusively out of the hydrogen and helium produced in the Big Bang 13.8 billion years ago. The problem is, being so massive, they tend to burn through their nuclear fuel supplies very quickly, in what astronomers jokingly refer to as the James Dean syndrome. They live fast but die young. And it's thought these behemoths would only have lived for 1 million years or so before going supernova. If stars between 130 and 250 solar masses could still form and exist today, they wouldn't live for very long. And their immense mass means that, theoretically at least, they're likely to die in what's known as a pair instability supernova. Now, this would involve the production of matter and antimatter particle pairs, primarily electrons and positrons. They're produced through collisions between atomic nuclei and high-energy gamma rays. Instead of mass being converted to energy in the star's core, the energy is being converted into mass, especially nickel-56, which eventually converts into cobalt and then finally iron. Now, this process would reduce pressure inside the supermassive star's core. And the drop-in pressure, which would occur during the star's luminous blue variable phase, leads to a partial collapse earlier than expected, and results in greatly accelerated nuclear burning in a runaway thermonuclear explosion which blows the star completely apart, without leaving a neutron star or black hole remnant behind. As well as SN 2006 GY, several other events, including SN 2007 BI, SN 2213-1745, and SN 1000 plus 0216, are all hypothesized to be possible pair instability supernovae. However, the alternative explanation suggests that SN 2006 GY may really have been a neutron star which underwent transformation into a Quark Nova, a precursor to an even more exotic object called a quark star. If that's the case, collisions between material ejected in the Quark Nova explosion and material already out there in the stellar envelope could re-brighten the supernova, allowing it to radiate at levels of increased luminosity for long periods. Quark novae are explosions driven by phase transitions in the core of a neutron star due to a process called quark degeneracy. Degeneracy occurs when subatomic particles such as electrons, protons and neutrons become so dense they can't be compacted into anything smaller due to the Pauli exclusion principle, which prevents two identical fermions occupying the same quantum state. Okay, time for a bit of background. The collapse of a Sun-like star into a white dwarf occurs because of electron degeneracy pressure, preventing the star from collapsing any further. More massive stars, beyond what astronomers call the Chandrasekhar limit of around 1.44 times the mass of the Sun, are big enough to collapse beyond the electron degeneracy stage, forcing electrons and protons to combine into neutrons and forming a neutron star. As with the electrons in the white dwarf, the further collapse of a neutron star is halted by neutron degeneracy pressure. However, if the collapsing stellar mass is greater than the Tolman-Oppenheimer-Volkoff limit, which is approximately 1.5 to 3 solar masses, which corresponds to an original stellar mass of say 15 to 20 solar masses, then the star could collapse beyond the neutron degeneracy phase, forming a stellar mass black hole. But if the star isn't quite massive enough to form a black hole, it might instead form an object called a quark star. A quark star is a hypothetical type of exotic compact star which, as the name suggests, is composed of quark matter. Okay, so what's quark matter? Well, it's produced when extremely high temperatures and pressures force nuclear particles to dissolve into a continuous soup or phase of free quarks. These are ultra-dense phases of degenerate matter, theorized to form inside neutron stars exceeding the Tolman-Oppenheimer-Volkoff limit needed for quark degeneracy. If they exist, quark stars would resemble and be mistaken for extremely dense neutron stars with unusually high gravitational fields. And like neutron stars, they'd be created through the destruction of high-mass stars in core collapse or Type II Supernovae. However, the existence of quark stars is still very hypothetical. That's because the equation of state of quark matter is still uncertain, as is the transition point between neutron degenerate matter and quark matter. It's been theorized that if neutron degenerate matter inside a neutron star is put under high enough pressure from the star's own gravity or from the initial supernova explosion, then it could break down into its constituent up and down quarks, forming quark matter. However, and yes, there are an awful lot of howevers in this story, it's not yet fully understood if this conversion is confined to the neutron star's center or whether the hypothetical properties of strange quark matter transforms the entire star into a quark star. Experimentally, the behaviour of quark matter is being actively studied in particle accelerators such as the Large Hadron Collider at CERN. The problem is this can only produce very hot quark-gluon plasma above 10 to the 12 Kelvin and only in tiny blobs the size of an atomic nuclei, which pretty well decay immediately after formation anyway. The conditions inside compact stars with extremely high densities and temperatures below 10 to the 12 Kelvin simply cannot be created artificially in a laboratory. So that means there's really no way of actually producing or studying the sort of quark matter expected to be found inside quark stars. I'm Stuart Gary. This is SpaceTime. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts, or Audio Boom. This has been another quality podcast production from Bytes.com.